In this video, we're going to look at the RL circuit, which contains a resistor and an inductor. So we start out by applying the loop rule to this circuit. So we start here and go counterclockwise. So first we go across the battery, we have plus E, and then across the resistor we have minus I times the resistance, and then across this inductor we have minus L times di dt. And this is equal to 0. So rearranging this equation and solving for di dt, we get this expression. And so the minute we close, or the instant that we close this switch and the circuit starts to run, the current is still 0. Remember, when we have an inductor, the current cannot change instantaneously, because the inductor is going to oppose any change in the current by Lenz's law. So at t equals 0, I is still equal to 0, and the current starts increasing at the rate E over L, because this I over here is 0, so di dt becomes E over L. And so as time passes, the current is going to gradually increase until the current reaches a constant value, which means di dt is equal to 0. And at this point, the maximum value of the current is just the EMF divided by the resistance, because we know when di dt equals 0, there's no potential difference across the inductor. Alright, so now we're going to find an expression for the current as a function of time by solving this differential equation that we got from the loop rule. Alright, so to start out, we're going to separate these variables, bring e minus IR to this side, and then the dt to the other side. So now we have to integrate both sides, and if we did a u substitution here, we would get a negative 1 over on the outside, and then this would integrate to the ln of e minus IR. On the right side, we just get 1 over L times t, and then plus c, the constant of integration. So now we can solve for c. We know that when t is equal to 0, then the current is equal to 0 as well, again because it doesn't increase instantaneously. So we can see that c is negative 1 over times the ln of the EMF. So now we can plug in the value of c to our equation. And then we can multiply both sides by negative to isolate this ln. Okay, now we can rewrite this because we know this is the same thing as saying e to all of this stuff is equal to e minus IR. So I'm going to e to the negative over LT plus ln e is equal to e minus IR. And using exponent properties, we can split this up. This is the same thing as e to the negative over LT multiplied by e to the ln e into EMF. And we know e to the ln of something is just that something. So this is the same thing as the EMF times e to the negative over LT. And then just rearranging stuff, we can find the final expression. I is equal to e over times 1 minus e to negative over LT. So if we were to graph this equation, then we would find that the current is increasing exponentially, and it increases until it levels off at this asymptote, which is the final value of the current E over E. And so we have, you can see at when T is equal to L over E, then the current has increased to 1 minus 1 over E of its final value, E over E. And this is a special time, we call it the time constant, which is represented by tau. So the time constant for a RL circuit is equal to the self-inductance divided by the resistance. And so you can see at this time, the current is 1 minus 1 over E times its maximum value. And so now we're going to look at when the current has reached its maximum value of E over E, and then say we disconnect the battery at this point. And so the current is going to be decreasing. But the current does not immediately drop to 0, because as we know, the current cannot change instantaneously when we have the inductor there. So the inductor is going to slow the decrease of the current by releasing the energy that it stored up in itself as the current was increasing. And so you could write another differential equation using the loop rule without the battery there. And if you solved it, then you get this equation for the current being discharged. So the current is equal to the maximum current, which is the initial current in this case, times e to the negative over LT. And so this graph would look similar to this graph, except that it would be decreasing and it would be approaching 0.